3. Like Malhar said, we'll start from week 10 and 11 first, and then we'll move to the earlier weeks after. So I'll just be in charge of, talking to you guys about Bayesian inference as well as correlation and regression. So let's get started. So can you guys, that is pretty small. Let's zoom in a bit. All right, that's way better. Okay, so let's start with Bayesian inference. So the way this works is just I'll go through bigger, smaller. Yeah, the camera will pick it up, don't worry. Yeah. So I'll go through some of the concepts. If you have any questions in the middle, just stop me and feel free to ask them. I'll be sure to allocate some time for the questions as well. So what is the idea of Bayesian statistics? So throughout most of your course, most of the course and most statistics in general, you handle an approach to statistics called the frequentist approach. And basically what the frequentist approach is that you're trying to find the parameter theta. This could be the mean in a normal distribution or lambda in a Poisson distribution. And in the frequentist approach, it is assumed that there is a true parameter for your mean. So at a population level, so for example, what is the average height for all of the students in UTSC? If you take the measurement of every single student and you take the average, that is the true, the true population mean. But obviously, that can't be done because no one has the resources to just measure everyone's height, so we take a sample instead. So the idea of statistics is to take samples, enough of them, and then basically the mean would converge to this true population mean. That is the frequentist approach. With that, we can construct a confidence interval. So for example, if we have a 95% confidence interval that mu is equal to, 160 centimeters for the average height of UTSC students. What that means is basically if we run the experiment 100 times, then 95 out of the 100 times, we would find the true parameter inside that confidence interval. A lot of statisticians, or at least some of them, argue that this is not a really intuitive way to understand what confidence intervals are, as well as how to actually understand what the true parameter is. Therefore, the concept of Bayesian statistics has been introduced, and this basically incorporates the idea of that you already have a hunch of what the actual parameter is going to be. So that is what is called a prior. So you already kind of know that the average height for students is probably somewhere between 150 centimeters to 170. So you can use that that intuition, that knowledge, to basically, that knowledge to create more distributions and see how, after your experiment, how it pans out. So you can read the idea later once the document has been shared, but let's go through some definitions. So the prior is the distribution of the parameter theta before we observe the data. So for example, the height we can say it's distributed uniformly between 150 to 170. And what this means is basically we just kind of have an idea that it could be somewhere in between those numbers. The posterior distribution is the distribution of the parameter after we have observed the data. So we have an idea, we run the experiment, we take our samples, and then based on that, we create a new distribution that combines the two to have a better understanding of where this true parameter lies. Moving on, the likelihood is basically the conditional distribution of the data. It's denoted as S, as how the professor is teaching it. Basically, S is just your sample. So the distribution of the data S given theta. Here are just some formula. I don't think you need to prove all of these things, but basically just know that this is what goes on in the background. So the marginal distribution of the data is basically given by the integral of the likelihood multiplied by the prior. So we call that MS. And then the posterior distribution is given by pi theta given s, that's the posterior. It's basically the likelihood multiplied by the prior and then divided by the marginal distribution. So the reason why we divide it is because sometimes when you multiply the likelihood and the prior, you don't get a valid PMF. Yeah. So the role of the marginal distribution is basically to normalize it and make sure that it's a valid PMF. But all you need to know is that since the marginal distribution MS is a constant, the main idea here is that the posterior is basically proportional to the likelihood multiplied by the prior. That's the whole idea of you have your intuition, you have your data, you combine them, and then you get your posterior distribution. So before I move on, does anyone have any questions about, yeah?
What's S?
Like I said, S is just the data, so it's x1 to xn. We just write S just because I don't want to write x1 to xn every time. Does anyone else have any questions about the idea of it? No? Okay, so we'll move on. So now that we have a better understanding of what the posterior distribution is, we can run some inferences on it. So just like anything else that you've seen in the course about distributions, you can find the mean, you can find the variance, and all of these things. So the same thing is applied for the posterior distribution. And we'll just go through some of the examples that you probably have seen before. So the first one is basically let the data be distributed in a Bernoulli distribution with the parameter theta. And then we have the prior where the theta itself is distributed uniformly between 0 and 1. Can someone just tell me what that means? Like, what does it mean that the theta is distributed uniformly between 0 and 1? Anyone? Yep.
The PDF of the distribution is just 1 if it's in 0, 1, 0 if it's not. There's no inherent bias towards any number.
Yep, exactly. So and then in the context of Bayesian statistics, it's basically we have a hunch that is somewhere between 0 and 1, and using the PDF of Bernoulli and uniform distribution, we can find the likelihood and multiply it by the prior, and you can get the posterior distribution, which is a beta distribution with those parameters listed. I'm not going to go into how you actually get these numbers because it is on the slides. I can't remember which slide it is, but in week 10, the professor goes through it. And then from that distribution, you can get the posterior mean as well as the variance. The mean is basically, if I'm not mistaken, is just alpha plus beta, and then it's alpha divided by alpha plus beta. So moving on, some other examples include if the prior is distributed in a beta distribution, and then you will get this posterior instead. And another one would be if the data is distributed normally where the variance is known, and then you're basically trying to see what mu is, or the average, and then you just have the prior of mu being distributed normally as well with mu naught and tau naught as its variance. And then if you do likelihood multiplied by the prior, you would get this long distribution, which is fairly simple. I'm pretty sure he went through that in lecture. You can just go through the slides to see how he came up with that. Moving on, now that we know how to calculate the mean, we know how to calculate the variance, and just the posterior distribution in general. There's something called a credible interval, which is basically a counterpart to the confidence interval in the frequentist approach. So a credible interval is basically an interval used to characterize the probability distribution. Come on in, just take a seat. It is defined such that an unobserved parameter value has a particular probability to fall within it. So as I mentioned before, a confidence interval, if you have a 95% confidence interval, it means that you can run your experiment 100 times And then 95 out of the 100 times that you've run it, you will find the sample mean is somewhere between the confidence interval that you have constructed. With Bayesian statistics and credible interval, that's not the case. Instead, the interval is basically just an interval of a 95%, for lack of a better word, confidence that the actual parameter lies somewhere between that interval. So it's not about repeated experiments, it's just that the parameter itself has its own probability distribution. And the way you get the credible interval is actually pretty simple. It's just how you normally calculate CIs, the intervals throughout the course. So for example, here in a location normal model, you just have, the mean here plus minus whatever your z-score is, depending on what percentage of the interval you want, and then multiply it by the square root of, by the standard error or the square root of the variance. So we've talked about credible intervals. The next one is the highest posterior density, or HPD. HPD is basically an interval where, as you can see in the picture, it's an interval where everything inside the interval has a higher probability than everything outside of it. So while a confidence interval usually is just equal on both ends, so for example, if it's a 95%, you get rid of 2.5% on each end. For the HPD, instead, you look at the graph, look at the distribution, and you basically get the 95% that is the narrowest inside, and that's the HPD. So that's just something you should know. And then finally, we are going to go through some types of priors. But before that, any questions about, intervals or the distribution itself? No? Okay, cool. So the final part of this section is basically the types of priors. So unlike the frequentist approach, as we've mentioned, the Bayesian statistics have this whole concept of a prior or your intuition before you even collect your samples, right? But a big question is, how do you actually choose this? How can you trust your intuition, and what prior is to be used? So there are three types that you can use. Number one is called a conjugate prior. So these are priors that will result in the posterior distribution belonging in the same probability distribution family as the prior. So for example, in an earlier example that we've seen, we chose theta to be distributed through a beta distribution, and that will yield a posterior distribution of another beta distribution. Same thing with normal. If mu is distributed normally with mu naught and tau naught, then the posterior mean given the data is also distributed normally. And finally, if the data is Poisson and lambda is distributed in a gamma distribution, that would also yield a posterior distribution that follows, the gamma distribution. So I wrote how here because there will be one question is, how do you actually get that? But we'll go through that later. So those are conjugate priors. Another type of prior is the improper prior. And basically, improper priors are priors where if you take the PDF, it doesn't equal to 1. So it's not an actual proper probability distribution. But why do we use this? We usually use this just because if we have no idea what to put for the prior, it's so for example, it's beta 00 is often used, and the intuition behind this is basically you don't want to know anything about it, which kind of ties into the non-informative prior as well. But just know that this is something that exists. But an important thing that you should know is that it's important to check that the resulting posterior actually follows a valid PDF or PMF, even though the prior doesn't necessarily have to be. And then the final type is a non-informative prior, which basically priors that has minimal influence. So for example, in our height example that we had, making theta follow a uniform distribution doesn't really tell anything about what we want the posterior to be. It's just something to fit in the, I guess, model of Bayesian statistics. And then just as a note, under non-informative prior, the posterior mode is basically the same as the MLE, but we'll get into more MLE stuff later. So yeah, those are the types of priors that can be used in a Bayesian statistic. Oh shit. What happened there? Sorry, just give me a second, guys. And we'll zoom in there. Yep. So like I said, these are the types of priors. Do you guys have any questions for this? Yeah.
What's a non-informative prior then?
So non-informative priors are basically priors that are used just to make sure that we have priors to be done to calculate in a Bayesian statistic model. They don't necessarily have to have any meaning to it. So for example, just like saying, the average height could be somewhere between 150 to 170. It's not really saying anything much aside from the fact that, it's a very, it's just not saying much. It's just the fact that you can have that between those ranges. So we have a few more minutes for this specific section. I'll let you guys do question 2. I think that's the easier one. I'll just give you a few minutes to try this, and then we'll discuss the answers right after. So do question 2 over here. I'm going to scroll up a bit just to show you what might be needed. You guys need more time? Raise of hands if you need more time. Okay, just do another minute or so. Oh yeah, sure. Okay, in the interest of time, I'll just take this question up now. So when I like to solve these problems, usually I just write down all the variables first before even starting anything. So can someone tell me what n is in this case? Easiest question. Yeah. Mm-hmm. Is this big enough or? Yeah, okay, cool. And then we'll just write everything else down. So we have that equals 1, mu naught equals 5, and then 0.5. So now we want the 95% CI. So we'll just basically plug in to the formula that I've showed you just now. And we will get plus minus 0.96. Okay, did everyone get to this part at least? It's just plugging in the numbers from the formula, right? And then if you just use your calculator and you punch those numbers in, you should get, I believe, this. Actually, wait, before I tell, did anyone get the answer? No? Okay, might have had not enough time then, but I'll just. Okay, so that's the answer for the 95% CI, credible interval in this case. We'll release the solutions when we share the document tonight, so don't worry about the steps in between. But just to finish this off, can someone tell me, with this 95% CI, what does that mean for mu? Like, how can you interpret it? How can you interpret if it's a confidence interval with a 95% confidence interval instead? That one? Yeah, that's okay. So for 90, yeah. Yeah, for normal. Mm-hmm. Sorry, go on. You're on the right track. Sorry, I can help you out. So for a confidence interval, basically means that if you take 100 different samples, 95 of them would have a sample mean. So in this case, the sample mean is 4, right? So 95% of them would have a sample mean that falls between these ranges. But for a credible interval, it basically means that our instead of running it 100 times, we have a 95%, again, lack of a better term, confidence that the actual parameter lies somewhere between these two numbers. So that's the two different like ways of viewing how it is, right? The frequentist is like you run it multiple times. For Bayesian, you only run it once, and then you see, okay, I'm like 95% sure that it's somewhere between these numbers. Okay, so that's just Bayesian inference in general. Does anyone have any questions about it? Yeah.
How do you get that formula?
The formula?
Yeah.
So it's, I'm sure in the exam it would be given. So it's this formula right here. Because you have your data distributed normally and your prior, which is mu, distributed normally as well. Through some calculation, you'll get a posterior with this specific formula, essentially, right?
Yeah, I didn't see that in the formula sheet.
It's in the slides. I'm sure if in the exam, he'll probably provide it, unless if you have to prove it, then you got to learn how to prove how to do that, which is just multiplying likelihood with the prior. Okay, moving on to week 11, which is correlation and regression. I'll like zoom by correlation because it's pretty easy, I think. It's basically if you have two variables, x and y, you're just trying to see how correlated these two variables are, right? And by that, it means that you're trying to see if, okay, if x increases, what happens to y? If it increases as well, it's positive. If x increases, y decreases, and negative. If there's no change, that means they're unrelated. I think everyone knows this through high school. This is pretty intuitive stuff. Something you should know about correlation, though, is something called the Pearson correlation coefficient. We denote it as the letter R. So the correlation coefficient is a number between -1 and 1, and it basically measures the strength and direction of the relationship between the two variables. So if R is -1, anything in the negative is a negative correlation. If it's a -1, it's a perfect negative correlation. And then conversely, if R equals 1, it's a perfect positive correlation. And if R equals 0, then that means there's no correlation at all. Here is a geometric definition of R. You don't need to know this, I think, so I'm just going to skim past that. So now that's the correlation. It's pretty easy. Regression is a bit more complicated, so we'll go through it slower. So least squares regression is basically trying to... It has the same idea, but instead of just correlation, you're trying to see if there's some significant relationship between the two variables. So if you let y equals b1 plus b2x be the equation of the line of best fit, we can see that y minus b1 minus b2x is just the deviation. So if you have a graph, and then you have all your points and stuff like that, and then you have your line of best fit like that, the deviation is basically measuring this distance between the actual points and the line of best fit, or like prediction, if you want to call it that. So how do we actually find the line? Our job is to find the line, and the way we do this is basically by minimizing this expression right here. So we have this graph. We have the difference between the actual and the predicted. The way we need to do it is basically get all of these distances, square them, and then add them all up. And then the line that has the lowest value after you square them and adding all up is the line of best fit, right? Okay, cool. So how do we actually minimize it? We already have y, we already have x. What we don't have is b1 and b2. Some books have it as b0 and b1, but for this course, I think Shahriar used b1 and b2, so we'll use that. And through some proof and differentiation, we can see that b1 is equal to the average of the y's minus b2 times x bar, which is the average of the x, where b2 is this formula right here. So it's just the summation of each individual x minus its average, multiplied by each individual y minus its average, and then all of that divided by the xy minus its average squared and the summation of that. So throughout stats, you'll be seeing this equation a lot. Before moving on though, some limitations of the least squares regression is that it assumes a linear relationship between x and y. So imagine your data is actually something like that, right? If you see this, would you fit a line to have a model to best predict the data? Yes or no? Just you can nod or shake your head. No, exactly. Why? Because it's not a line, right? It's a parabola instead. So if you have a line like that, it's not telling you anything about the data. So least squares regression assumes that it is the data point is a linear relationship. It's also sensitive to outliers. So for example, if you have all of that, and then suddenly you have one here, this distance is going to affect your minimization so much, right? So instead of having a nice line through all the data points, it'll be shifted somewhere like that instead, because it's trying to get to that singular outlier. Also, it's unreliable if it's not evenly distributed. And for higher dimensions, it's not taking into account if, two different x's have any relationship with one another. But that's not needed for the course. So now we're moving on to regression under... Sorry, before that, does anyone have any questions about the basis of regression? No? Okay. So moving on to regression under normal distribution. This is the case where you have multiple points of x, and then for each one of those x's, you can assume that there's a normal distribution laying on top of it. So, for example, you have y, you have x over here. What's the example I use here? So x is height, y is weight. Let's see, per height, what's the weight? So let's say 150, 160, 170, and 180. And let's say the data is distributed like this. As you can see, between x and y, there is a relationship between them, right? As x increases, y increases as well. But with this section specifically, we need to realize that for each x, this has a normal distribution on its own. So knowing that, we can see some of the assumptions or notations that we'll be using moving forward. So y per given x is normally distributed with beta 1 plus beta 2 squared as the mean, and then just a sigma squared variance. The mean of y is a linear function of x. That's easy to see. The variance is constant. That's actually quite important with this as an assumption. And then, the y's are the observed values of y, the x's are observed values of x's, and the y's are all independent. Those are trivial. And then with this, we can prove that the expectation of y given x being one of those is just beta 1 plus beta 2 xi, as we've defined. The variance is all sigma squared, and the likelihood is what is shown on screen. The way you can get this is through multiplying all the PDFs together, just like how you get a normal likelihood or calculating MLE. But why is this important, right? Why is the likelihood important specifically? With any model, we want to maximize the likelihood. Now, with this formula of the likelihood, the way we can maximize it is actually by minimizing this section right here. If we minimize that, then, let's say it's minimized to 0, then this is just e to the 0, which is 1, and then you can just maximize this. But if it's more than 0, it's closer to a bigger number, then this value right here would basically bring the entire likelihood value down. You can just plug in numbers to see that. I won't get into much detail on how that works. but basically what you need to know is that you want to maximize the likelihood, and to do so you minimize this, this part right here, which is the least squares that we've seen before. So I'm not sure what the exam is gonna ask you about, but I've taken one class with Shahriar, and he likes to ask you like interpretation questions. So be sure to revise that and actually understand what the betas signify. So the interpretation for this model specifically for beta 1 is the expected value of y when x equals 0, and that's very easy to see. Like if you have, it's beta 1 and 2, right? Yeah. Beta 1 plus beta 2 xi. So beta 1 is basically what y1 is if this is 0, right? Because then it just cancels out. So yi equals beta 1. Beta 2 is the change in expected value of y when there is a 1 unit increase in x. So for each unit increase in x, beta 2 would represent what the difference is in the value of y. And this is y equals mx plus b, but like, more complicated. So if you have x equals 0 and then you have another equation where x equals 1, you take the difference between that and you can see beta 2 represents what the changing in value is for y. That's a small remark there, but we won't go into that now. So yeah, moving on, we have just a small table to show you what the difference is between parameters, estimators, and estimates. Parameters are the true values that you're trying to find. So these are usually Greek letters. So in this case, beta 1 and beta 2. Estimators are things, are variables to use to estimate the actual parameters. These are usually non-Greek letters and capitalized. So in this case, B1 and B2. These are the random variables that you're investigating. And then there are estimates where it's also B1, B2, but lowercase. And these are the actual values that you calculate in your samples. So we've seen before, B1 equals y bar minus B2 x bar. And then B2 is this whole equation over here. And then we can see that B1 and B2, since they are random variables, they also follow a distribution, and they actually follow a normal distribution. And that distribution is given here. I don't think you need to know how to prove all of that, but I've attached a link here if you want to see how they obtain those values. So you can see B1 follows a normal distribution where it eventually converges to beta 1, and then that long variance over there. And then B2 converges to beta 2, and that variance which would play a part in a bit. So does anyone have any questions? No? Cool. So now we can look at the confidence interval, not credible, but confidence interval for beta 2. And the reason why we're more interested in beta 2 is because it's the slope as opposed to beta 1 where it's just the intercept. So just recall that the unbiased estimator for a population variance is the sample variance, where it's this formula right here in the context of regression. So instead of x minus x bar for other purposes, we actually use the deviation that we've discussed before. Through some proof, we don't have to get into this. You can see this fact right here. And it actually, for beta 2, it actually follows a t-distribution with n minus 2 degrees of freedom. And with that, you can have a confidence interval such as this, which is B2 plus minus the t-value with the standard error, where the standard error is just the square root of the sample variance divided by that expression over there. So now that we know how to calculate the confidence interval for it, we would basically conduct some hypothesis testing to see whether beta 2 equals to 0. Can someone tell me what it means if beta 2 equals to 0? Yes?
No linear relationship.
Yeah, correct. So if beta 2 equals 0, then that means there's just no relationship between x and y. So how can we test this? So there are two ways to do it. One simple, but I don't think it's fully correct way, is just to calculate the CIs and then just check whether 0 is in the range of CIs. I don't think that's robust, but that's something that's been discussed in the course. The other more robust way is basically to calculate the test statistics t, where it's equal to B2 divided by its standard error. This is pretty usual in statistics, to just get the estimate divided by the standard error to get your test statistic, and then you compare that with the value of whatever distribution. So in this case, it's the t-value with n-2 degrees of freedom. And then you can calculate the p-value, or you can just use the test statistic to compare. And then in summary, basically, if any of these things happen, so if 0 is not in the confidence interval, or the test statistic is bigger than the t-value, or the p-value is less than 0.05, which is what we usually use, then you just reject. That means there is a significant relationship between x and y. If those things don't happen, then you don't say that you accept your null hypothesis. I think you guys know this. You just say you failed to reject it instead. What time is it? Okay. Moving on, we'll talk about some decomposition and then the coefficient of determination as well. So calculating all of these numbers and all these variables can be quite taxing computationally, whether you're calculating it by hand or even by using a software. An easier way to do it is through using decomposition, and that's not the only use of decomposition, but for our purposes, that's it. And there are three. There's the total sum of squares, or TSS, regression sum of squares, or RSS, and the error sum of squares, or ESS. And those are the formulas respectively for all three of them. And then we can see that basically the total sum of squares is equal to the regression plus the error sum of squares. And this is pretty intuitive if you think about it. Basically, the total sum of squares of your entire model is just what can be explained by the model plus any error that your model can't be explained, right? So that's pretty intuitive if you think about it that way. And then using these values, you can calculate what is called the coefficient of determination, or R squared, not to be confused with the correlation coefficient, which is small r. This is big R squared. And you can calculate this through the regression divided by the total. So you're just explaining how much your model, you're just showing how much your model can explain the underlying pattern of the data, right? For a simple linear regression model, when there's only one x variable, you can also show that the small r, the Pearson correlation coefficient, is actually just the square root of the R squared here. Here are some remarks about this fact. You can read it later. And then you can also show that, like, for the sample variance, you can just calculate it through TSS minus RSS divided by n-2. So that's pretty intuitive, I think. Does anyone have any questions for that? Yeah.
Why is it t greater than t n-2?
Why is t? So if t is greater than t n-2, then it basically states that your test statistic is in the rejection region. Wait, sorry. Yes. So it's more extreme than your critical value, right? So yeah, for a two-sided test, I think t distribution is symmetrical, right? Do you guys know? I can't remember. Let's see. T distribution. Yeah, looks symmetrical enough to me. So if it's and then here's your critical value. And then if you calculate your test statistic and it's somewhere in here, then you basically reject your hypothesis that beta 2 is equal to 0. Anyone else have any questions about this? No? Okay, so just one final section, which is regression with a categorical variable instead. So everything we've discussed so far is numerical. You have numbers, x is a number, y is a number, and then you just kind of map them to each other and see, what happens then. But if x is a categorical variable, then it's a bit different. So for example, if x is whether someone is male or female, or like x is someone's favorite color, it could be red, blue, or green. Something that you can't really quantify on a normal number scale, then you do something slightly different, which is creating a dummy variable to act as a numerical representation. And what this means is that if you look at the table here, each row is an observation, a person, and they could either be male or female in this case. You can create this dummy variable xf, and then if they're male, you just put 0 because they're not male, and then if they're female, you put 1. So 1 yes, 0 is no. And then using a normality assumption, we just get our normal model, which is pretty much the same as we've seen so far. The only difference is that the variable that you use instead of a normal x, and then you plug in real numbers, the x only holds the value of 0 or 1. And this creates really cool interpretations, which is that you can see here that in the second line, the expectation for y if x is male student, then it's just beta 1. That's the average value for y if they're male, because you just plug in 0 for x, and that will cancel out beta 2. If the student's female, then you plug in y, and then the average value for y, given that the student's female, is basically beta 1 plus beta 2. And the difference between the two averages, if you just do really basic math here, is beta 2. Now, as I mentioned before, Shahriar likes to ask you questions about interpretation, so just be sure that you know how to interpret beta 1 and beta 2, as well as beta 1 plus beta 2, because these are all different things, and it can get confusing sometimes. And then with that, you just can run normal hypothesis testing to test for beta 2 is equal to 0. If it's rejected, that means x and y are related. Now, what if x has more than 2 categories? So we're still dealing with one variable, but you can have multiple options. So here we have male, female. Below here you have university, high school, and kindergarten. So there's 3 different values that x can take on. What you can do is create more dummy variables for each one of those options. So if it's university, you just create x university, x high school. If the person goes to university, you just put 1 in that column and then 0 everywhere else. And then same thing for high school. And then if it's kindergarten, you just put 0, 0 for both. You don't need a kindergarten column. And here I just gave you a bunch of interpretation for the betas in this case. Just know that, just go through this. It will make more sense with practice, I hope. And I'm pretty sure that your exam is going to have at least one of these questions of interpretations. We are running out of time. So I have a few questions here, but because we don't have time to go through them, I'll just post the solutions when you guys get a document later. I'll just give you guys one question, which is this R output. This is from the slides, but just to give you guys a refresher of how to read it. So based on this R output, can someone tell me what is beta 2? This is not a categorical model. These are just a normal regression model. So I'll start off with an easier question. What is beta 2? Is it a parameter? Is it an estimator? Sorry, not beta 2, B2. It's not a parameter. A parameter is, so parameters are usually Greek letters. So did I say beta or B? If I said beta, my bad. So I'm just asking for B2, so what you actually observe. Yeah, it's an estimate, right? Because you already have your numbers and you can see what the actual numbers. So you just look under the estimate column, and then for B2 specifically, it's not the intercept, but it's X. So 2.0591 is B2, okay? You need to know this because our questions is something you need to be able to interpret and read. So that's B2. Can someone tell me what is the standard error for B2? .1023, exactly. So it's the same row, that's the B2 row, and then it says standard error as the column. So that's the standard error. Now, can someone tell me how to get this value over here? 20.135. That's the t value. But based on what we've discussed so far, I'll scroll up a bit in a while. How can we get this 20.135? It is the test statistic. What numbers do you? What's the formula? It's on screen right now.
B2 minus beta2 divided square root and what? And SE.
Yeah, so it's the standard error, right? So it's this one right here. So you're correct. You said B2 minus beta2. When we're doing hypothesis testing, beta2 is 0, right? So it just simplifies down to B2 divided by its standard error. And we know what B2 is, and we know what its standard error is, which is this and this. So if you divide 2.0591 by 0.1023, you will get this value of 20.135. And since 20.135 is bigger than the t value, which is I think around 12 something, it would be significant. Another way to see is that if there's 3 stars here, that means it's significant. That's the p-value. So be sure to brush up on how to read the R table, and because like that's the easiest way to basically get your test statistics or get your beta value, your b value, or the standard error. What courses have done in the past is that they blank out one of these values and then they ask you how to get those values. So if you don't have the standard error, then you just you divide this by this, the estimate by the t-value, right? Okay, cool. There's a bunch of other questions here that you guys can practice, and the solutions will be up as well. But that's it for me. I'll hand the, are we taking a break? Yeah, so we'll take a 5-minute break, and then we'll come back at 5:09. Thank you.
We're going to start, so I request everyone to take a seat. Excuse me. Can I get you guys to sit down? Thank you. Okay, so Aniki's part, week 10, 11, were sort of independent from what you've been doing, which is, unbiasedness and estimators and Fisher information and stuff. So I'll be sort of starting with some things that you learned in the middle of your post-midterm lectures. Mainly, we're going to start with score and Fisher, and then we're going to keep on going. So we've seen likelihood. We've seen likelihood for an IID sample. We've seen, thank you. We've seen log of likelihood. And what does likelihood and log of likelihood inherently represent? What does it mean for those values to be high or low? Do we have any idea? Does it, in a sense, represent like how well this sample conforms to the underlying distribution? In a sense, yes, right? And the score and Fisher information are sort of along this same wavelength where we're trying to identify how good our estimator is or how good a particular sample is corresponding to the underlying distribution. So the score of a parameter, right? It's a function of the parameter given some sample, is nothing but the derivative of the log likelihood of that particular sample. Nothing more, nothing less. Okay? What we know is that the log likelihood is maximized at the MLE, right, by definition. So what would the derivative be if it's maximized? So if at, let's say this is your MLE, its maximum, so it has to be like less everywhere else, right before it. What can we say about the slope? It's 0, right? So the score is 0 at the MLE, right? Okay, very nice. That makes sense. Additionally, instead of if we aren't just taking one sample, if we're taking many IID samples, let's say you have n of them, what is the score of this entire sort of sample? Well, we know that the score is nothing but the derivative of the likelihood, and we know that the derivative of the log likelihood, and we know that the log likelihood of IID samples is just the sum of the individual log likelihoods of each independent sample. What does that mean? I have like this derivative partial over theta, and you have sort of this summation of the log of the likelihoods, right? Log of whatever f theta given x. The point that I want to make here is that when you take the derivative of like f of a plus, and then let's say you have two functions, f of x and g of x. If you take the derivative of f of x plus g of x, it's just the derivative of each one individually, and then you just add them up. So because it is IID, the score of this sample, which is more than one, is just the sum of each individual score. Right? Does that make sense? Great. It's by linearity of the log likelihood, and then the fact that you can break your partial derivatives for a linear sum. Right? Okay. I have a really tiny example for this. And this is straight from your lecture slide, so it's not something new. It's good to revisit this. So suppose you have some a sample which contains, which was created from the Poisson distribution. You have n data points. They're all IID. What is the likelihood of this? The likelihood is the product of the each individual, the PDF, right? And what's the PDF of Poisson for xi? It should be something like e to the power minus lambda xi, or lambda to the xi over xi factorial. Right? This is your PDF. Good. So the log would all the log would do it would make this product into a summation, and then the minus lambda would come down, and then the xi would come down. You'd have ln lambda, and then you'd have minus ln of xi factorial. I've done that for one particular example instead of showing it for the entire sample. And the score is nothing but the derivative of this. So if you derive this with respect to lambda, which is our parameter in this case, this becomes minus 1. There's no lambda term here, so this is 0. And then the ln lambda becomes 1 over lambda. Now, the theorem, this one, says that if it's true for 1, then for the sample, it's just the entire sum. So I just have to multiply this by n, which gives me this. Well, actually, not multiply this by n. It's the sum for the score of every xi. So I have to take the sum of all possible xi's. Right? OK. So that gives us sort of a feel of what the score is. You can try and do it this way, where you have all of them. And if you expand it and then you work it out, you get the same answer. Right? Basically, as a hint, e to the power minus lambda, when this is multiplied, is e to the power minus n lambda. And then the n lambda is going to come out when you take the log. And then when you take the derivative, you'll have minus n, just like there, right? Cool. Additionally, we know that the MLE score is supposed to be 0. So what value of lambda actually gives you a 0 over here? Well, it's the average, right? So minus n plus summation xi over summation xi over n. This cancels out, and then you have minus n plus n, which does indeed give you 0. So that would make the average the MLE, right? So if you were given a score function and asked to find the MLE, you could solve for the score equals 0, and then work backwards and find the MLE, right? Okay, great. Now the score function isn't solely dependent on lambda. It depends on your observation, right? In particular, for this Poisson example, it depends on the sum. So if the sum changes, the score changes, right? Right? The function changes. So take a look at this example. So you have 365, which adds up to 14, and you have 539, which adds up to 17, right? Now, if you were to assume, so under the assumption, you can see that the average of 17 is what? Divide by 3, like 6 point something, right? 6.33. And that's where you're getting the peak. That's where the slope is 0. Whereas in this example, where the sum is 14, the average is 4.66, and that's where you're getting the peak. 4 point something like that, right? Okay. So the sum changes the observation. Now here is some, this is another point, and we're not going to prove it because it requires you to do some things. But this is an important thing. If you're allowed to interchange derivatives and integrals, in addition have like a couple other requirements that are satisfied, the expected value of the score over every possible sample that you can observe ends up being 0, right? And that is true only at the true parameter, right? Cool. We can see this will be true for the Poisson example. Well, then we should actually do the Poisson example. So we already have the score. All I have to set is, or show is that its expected value is 0, right? At the MLE. Or no, I just have to show its expected value is 0, which should be fine. Add the true parameter. So let's see. The score is minus n plus summation xi over lambda. What is the expected value of this? It's minus n plus 1 over lambda, summation of expected value of xi. What allows me to do this? Well, it's a summation, right? I can break it apart. Cool. What is the expected value of any parameter, of any observation, given that the observation comes from Poisson lambda? What's the expected value of that? No, x bar is an estimator. Lambda, right? The expected value of xi is just lambda for Poisson. So then what do we have? And lambda. Lambdas cancel out. You get 0. Lovely. Okay. Questions? Okay. So if there aren't any questions, we'll move on to this part, which is the Fisher information. The Fisher information is defined in 2 different ways. It's defined as the inverse of the derivative of the score, or the inverse of the expected value of the derivative of the score, which is this rightmost thing. Or it's also defined as the variance of the score, right? And what I'd like to sort of point out, like what the intuition is behind this Fisher information, the higher it is, it means the higher the variance you have for a particular xi. What that means is for a small, if my xi was slightly different, I would end up getting a much bigger difference for the score, right? So we talked about, the MLE having a slope of 0. But let's say I have two kinds, right? I have this, and then I have a much sharper one. Sharpness is good because it means that a small perturbation over here yields a large difference in the y value, right? So what if this is your just log likelihood, then the derivative is the slope at some point. The double derivative is the rate of change of the slope. So how fast does it curve, right? This curves a lot faster than this. This means this has, if I were to get one extra sample point here, I would get a lot more information, right? So that's why it's called Fisher information. It sort of quantifies how much a single observation can impact your estimate of the true parameter. Why do you have to do the expected value is whatever. Why do you have to take the double derivative of the log likelihood, which is this, and have to take the negative? Well, because this value, if it's a curve like this, what can you say tell about the double derivative? It's negative, right? So you just switch it so larger is better, and your value is always positive. Okay. Cool. So one more thing. If you have an IID sample, then the Fisher information, which is just the variance of the score, because it's IID, just becomes the sum of the Fisher information for a single observation. So you have that relationship, right? Any questions? No questions. I'm going to skip on examples. If there's time, I will go back and maybe I'll even pull up the slides and take up a few examples from there. But till then, we're just going to keep going on this sort of review. Okay, so since there aren't any questions, we'll be moving on to chapter number 3, where we're going to be talking about how the maximum likelihood estimate behaves in general when sort of you end up taking more and more samples, right? And if we can figure out how the MLE distribution is, or how the MLE is distributed for large values of n, we can then sort of start testing, right? Because if we can claim that the distribution follows some normal, then we have like a confidence interval, and then we can compute the p-values, and we can do all that jazz. Okay, so there's this large sample property of the maximum likelihood estimate that says as the number of observations in your sample increases, as n tends to infinity, the score converges in distribution to a particular normal with mean 0 and variance n times the Fisher information. And you also have this. This essentially says that the maximum likelihood estimate approaches the normal with approaches in distribution with mean equal to the true parameter, right? And the variance is equal to 1 over ni, or 1 over n times the Fisher information. Okay. So what is the consequence? The expected value is theta naught. This comes straight from this. So this is sort of like the standard normal, but if you bring it back, and if you just look at the distribution of theta hat minus theta naught, you would see that it's a normal distribution with mean 0. So if a minus b has mean 0, then the expected value of a is whatever, b, right? Similarly, for large n, the variance is this. This also follows from the second point. If you don't recall anything from this chapter, but you remember those two things, you can recover everything else. Okay, so those two are very important. Okay, the maximum likelihood estimate is asymptotically unbiased. Does anyone know what asymptotically unbiased means? Yeah, as your sample approaches infinite in size, it becomes unbiased, right? So can we show that? Well, it's already shown, right? Okay, so you have unbiasedness. You can just check that the expected value of theta hat is equal to the two parameters. So literally 0.1 is showing it's asymptotically unbiased. We just rewrote it. MLE is a function of sufficient statistics, and MLE is consistent. This is something that Bob will take up after I'm done talking, what it means to be sufficient, what it means to be consistent. So I'm going to skip those. And the maximum likelihood estimate is asymptotically efficient. This is something I'll cover maybe in 5 or 10 minutes. So I'll wait on this one too. Okay. The MLE-based confidence interval for theta naught, your true parameter. What can we use? Well, we can use this, or we can use this other one. We can use one of these two to compare, right? What would our confidence interval be? Well, we know that it's normal, so then using the normal, we can derive the z value, and then from the z value, we can figure out a confidence interval, right? So this is exactly your pre-midterm stuff. It's just applied to this sort of weird-looking statistic, I guess. So you'd start with the MLE, and your variance is 1 over ni, and then you would do exactly the same thing as you've done up until now, where you would take, depending on what your p-value is, what you want, or what your alpha is, 1 plus gamma over 2, or 1 plus alpha. This is, by the way, this is two-sided, right? That's why we're doing the divide by 2 as well. Over ni theta naught, right? Does anyone know what just this term is called? We did this before. Well, you have the MLE, and then you have some, what's it called? Yes, Bob. The radius? Close enough. Close enough. It's sort of like how wide the confidence interval is. Sorry? Correct. Margin of error. That's great. You get a candy for that. So that's your margin of error. You compute this, and then so don't even bother writing this out. Just write the margin of error out, compute it, and then once it's a constant, just do whatever, MLE plus minus that, and that's your confidence interval. Okay. A problem with this particular case is that we don't have the true parameter. So how are we supposed to actually compute the Fisher information if we don't have the true parameter? So you have to take an estimate. What's the best estimate we can take for the true parameter? Any guesses? What's the best estimate we've seen up until now? What's it called based off of likelihood? Yeah, the MLE, right? So you would estimate with the MLE. So there's two kinds of estimates. You can either plug in the estimates over here. So this is pertaining to the Fisher information, right? So this Fisher information, you can either plug in the MLE over here instead of the true parameter, or you could go a step further and you can say, I don't care about the expected value of this double derivative. I am just going to take a look at my current sample and then compute the double derivative, and I don't care about the expected value. What I have right now is a good enough estimate, and I'm just going to plug it in right here. Right? So there's two kinds. We're only going to be doing observed Fisher information because that's what your professor has told, right? That you're going to be focusing on the observed Fisher information instead. Okay. So now what's changed? Well, we don't need the true parameter anymore. In the margin of error, we're just going to use the MLE. That's it. Nothing else has changed. Cool. Questions? Any questions? No questions? Great. Efficiency. So let's say you have some unknown parameter theta, and you have two estimators for it. How can you figure out which one's better, right? Well, first, you want it to be unbiased if possible, right? So you want the expected value of this estimator to be equal to the true parameter. And let's say that's true for both of them as well. What's the next thing you can do to compare them? They have the same expected value. Yeah, the variance, right? You can compare the variance, and the one that's smaller means it's more likely for it to be, the bound around the true parameter is tighter, which means it's better because there's a higher chance that you'll find it quicker with fewer samples, right? So tinier variance implies more efficient under the assumption that the both of these estimators are unbiased, or they have the same bias. Either case, if their bias is identical, then the next step to compare between the two to figure out which one's better is the variance, right? The efficiency is just a quick and easy way. It's sort of like taking the ratio so that you just have one number, and if it's greater than 1, that means the denominator is smaller, which means the denominator has less variance, which means the corresponding estimator is more efficient, is better, right, compared to whatever the estimator you have on the numerator. Okay, cool. Does this make sense? Why we're doing this comparison and why taking the ratio and then just figuring out greater than 1, less than 1, equal to 1 is a little bit quicker? Great. So we're going to end this chapter off with a pretty nice inequality. It says, if you have an unbiased estimator of some true parameter, then the variance of that must be at least 1 over n times the Fisher information, right? And the proof of that ends up showing you create a z, which is like the score function, and then you have to somehow show that the covariance between t and z is equal to 1. We're skipping that. Just realize that you have this. And what this means is if you have an estimator that has this variance, it's as low as it gets. There's nothing better, right? So if you have an unbiased estimator with variance equal to 1 over n times the Fisher information, that's the lower bound. You cannot get another estimator that has less variance, i.e. that is more efficient. You found the most efficient estimator out there, or one of the most, right? Okay. We showed that the MLE is unbiased. We've already done that. And we also showed that the variance is 1 over n times the Fisher information, right? I believe we do that over here, right? It follows from this second point, this convergence of distribution. So the MLE is asymptotically efficient. It's as good as it gets. When n tends to infinity, it's one of the most efficient estimators that you can have. Okay, cool. Questions? No questions? Great. Let's move on to the last chapter that I'll be doing today before I hand it over to Bob. And this is about testing the model fitness. Like how well does the given parameter fits what I'm seeing, fits what I think the underlying distribution is. Okay. So there's two kinds of tests, and there's not a lot that's different between them. In the first one, notice that it's very similar to this value over here. The only thing that's different is in this you have the Fisher information using this unknown true parameter, whereas in our case, we just use the MLE instead, right? That's the only difference. So we can use this test statistic, and it's essentially that result, but we're using the MLE. And the score test is slightly different. Instead of worrying about this evaluating at the MLE, we instead evaluate at the null hypothesis, whatever that is. and we use the score instead. So that corresponds to the first one, right? That corresponds to this first thing over here, right? Does everyone see why the first equation over here, which is this one, and this equation over here are identical? It's just I'm just normalizing, right? That's all I've done. I'm just normalizing. So in my WALD stats, I know that for Bernoulli, the MLE is just the average. So I can just plug in the average into the Fisher information. That's all I have to do. And for the score test, I have to compute the score. Lo and behold, you'll still see the average show up in the score. Okay, don't have time to go over this. I don't think so, but if I have a chance, I'll get back to this. Okay, likelihood ratio tests. So first of all, where's the word ratio coming from? It's because we're taking some sort of ratio. And we're taking the ratio of what? Of the likelihood over what? Over some parameter space. So what the LRT is supposed to do is, suppose you have two sort of hypotheses. The first one is that the true parameter belongs in, I don't know, this range, right? Let's say 1 to 2. And let's say my second hypothesis is that the true parameter belongs in the range 2 to 3, right? And I want to see which one's more likelier. Well, what I can do is I know that there's a way for me to compute the likelihood for all different, parameter values, right? I can put in L of 1, 1.5, 2.7, whatever. What I'm going to do is I'm going to take the best one in each individual, subset, or not subset, it might be continuous, so subregion. And I'll take the best one in both and compare their bests of the two regions. And then if the numerator is better, I'll get a ratio that's bigger, right? So what would that imply? That would imply that it's much more likelier that the true parameter is in whatever, omega naught rather than omega 1, right? So it's just sort of like a comparison. Why am I calling it a parameter space and not like a range? Well, actually, your parameter could be like a set of values, not just a single value, right? It could also, I don't think it can be discrete, but I don't think we should worry about it being discrete. Okay, so a small value provides evidence against this null hypothesis. Why? Well, that means the max over some other region is much, much larger, right? So the probability that it's in omega 1 is much, much larger than the probability that it's in omega naught, which is your null hypothesis. So at that point, if your I guess A star is tiny, you would choose to reject your null hypothesis, right? Okay. What happens if your parameter space in the denominator, which is your alternative hypothesis, is literally everything, is the entire possible set of values that the parameter can be? Well, what's the largest you can get? By definition, it's the MLE, right? The maximum likelihood estimate is the largest possible likelihood you can get, is the parameter that maximizes the likelihood. So if you don't have a restriction of omega naught, then you just get the MLE as your denominator. And when you have the MLE as the denominator, if the MLE is contained in the omega naught, then the maximum will again be that MLE and the ratio would be 1. But if it isn't, then you know that it's going to be less than 1. So the numerator is going to be tinier than the likelihood at the MLE. Okay. So let P be the dimension of your parameter space. In this case, just assume it's 1, right? The easiest example is to work with 1. And D is the dimension of your null hypothesis, which is the number of free parameters under the null hypothesis this would usually be 0, and you'd get sort of p minus d equals 1. You'd get chi-square with 1 degree of freedom. This result, I'm not sure if it's been derived. Has it been derived in class? Yes? No? Do we know? It hasn't. Okay, but this exists. And using this, we can come up with a test, right? So if you were to compute this ratio and then take the log and then multiply it by -2, it converges in distribution to this chi-square with p minus d degrees of freedom. Okay. Does that ever come into play? Yes, over here. Questions before we move on to this last component? Okay. Well, P is defined as the. Let me read so I don't make a mistake. P is the dimension of the entire parameter space, right? Versus D is the dimension of the null hypothesis. What this means is, let's say my null hypothesis wasn't a region. Let's say my null hypothesis was that the true parameter is equal to, I don't know, 5. Right? What's the dimension of this? It's a point. The dimension of it is 0. Right? It's fixed. Versus my entire parameter space could be whatever. 0 to infinity. In which case this would have dimension 1. Does that make sense? Cool. So then this is P equals 1. In this case, your D is 0. P minus D is 1. Okay. Cool. What does 0 degrees of freedom mean, by the way? Do we know that? What does intuitively 0 degrees of freedom mean? Yes. Not exactly. It's not about the mean. It means there's no variability. It's fixed. Here's an example. Let's say my parameter could be anything, right? Let's say my parameter could be any positive real or non-negative real. So this. If my hypothesis is also the same thing, well, we know this to be true, so this is trivially true. What is your A star? It's just 1, regardless of what this is, right? This is D, which is 1, and P is also 1. P minus D is 0. There's no variance. There's nothing. It's fixed. It's always 1, right? Okay. Cool. Goodness of fits. The chi-square goodness of fit test is for figuring out categorical random variables. There's a small typo over here. This should be k. So if you have x1 through xk, which are counts of your observations, so your observations, let's say you had 10 million observations, and then there were like 10 categories, and then you don't really care about the 10th observation being whatever category A and the 11th observation being category B. You just want the total counts. So you can sort of like take a general sort of like a histogram style approach. Because that's all that matters actually for this categorical variable. Then these random variables that were generated from the sample follow the multinomial distribution with some priority, with some probabilities, right? The goodness of fits test is essentially saying if I were to sum up this ratio, the observed count minus the expected count divided by the expected count, and if I were to sum it up for every single category, it would converge in distribution to the chi-square with k minus 1 degrees of freedom, right? How do we actually use this? I guess, okay. That's not given. Whoops. That's not given, so I'll probably take that example up. Okay, so if you don't know the actual probabilities, which you normally won't, you need to estimate it under some parameter theta, and usually your best estimate is your MLE, so you would take your MLE, right? And you would still get the same thing. Cool. One thing you have to notice that is because you're actually estimating the parameters, you're taking up some degrees of freedom. So the degrees of freedom does reduce by however many, whatever the dimension is for your parameter space, right? So if your parameter space has dimension 4, then your degrees of freedom would reduce by 4. Cool. That's it for my part. But before I hand it off to Bob, I think it might be beneficial for doing a couple examples. Or do we want to take a break? Well, what are we feeling? Raise your hand if you think a break is nice. Raise your hand if you think a couple examples would be nice. Okay, let's do that. Aniki, do you have the slide open? No? Okay, that's fine. Let's do, yeah. While you do that, I already have like one example written up. And then you can just pull up the slides. By the way, are cheat sheets allowed for you guys? No? Okay.
Before I pull up the slides, please don't judge my wallpaper.
You can just disconnect it.
Nah. Which weaknesses?
Oh, this is week 9. Week 9 is the examples that are worth doing, actually. Yeah, okay. Cool. All right, so then I can just pull it up over here then. Where's the walled test? There we go. So what would the walled test be for this? Okay, so let's not have any of this here. Okay, so we want to figure this out where the observed Fisher information, so SE at MLE is just square root of 1 over n times this observed Fisher information, this value over here. To be able to do that, I first need the Fisher information. To be able to get the Fisher information, I need the score. To be able to get the score, I need the log likelihood. To get the log likelihood, I need the likelihood. So let's start there. Let's start with the likelihood of this sort of observing this Bernoulli sample. What is the PMF? Or, yeah, what is the PMF? What do we have? Anyone? Yes. 1 or 0? Well, it has to be some formula. It has to be with respect to theta, right? What do we have? Yeah. So for a particular xi, when you write your likelihood, it's theta given x or x given theta? I believe it's x given theta, right? I'm just going to use theta comma x. You can fill it out later. I keep forgetting. Should be theta to the power x times 1 minus theta to the power 1 minus x, right? Something like that. And if you have many of these, what happens? You take the product, which ends up being the sum in the numerator. So you would just get this. x1 to xn, theta to the power summation, and then n minus summation. Right? Okay, what would that make our log likelihood? With respect to theta. It would just be the log of this, right? So it would be summation x log theta plus n minus summation x log 1 minus theta. That's all I did. I just took the logarithm, right? Let's make sure that actually makes sense with the slide. It does. Point number 2. Cool. So we have this log. Next step, find the score. So derive that with respect to with theta. So derive that with respect to theta, the score. Summation xi over theta plus 1 minus theta. So when you take the derivative of this, you get 1 over 1 minus theta, but you also get a negative sign just for the theta, so that comes out minus, and then you have n minus summation xi. Okay, are we done? No, we need the MLE, and we need the Fisher information. Let's find the MLE first, and then we'll find the Fisher information. So to find the MLE, you need to equate this to 0, right? So let me just substitute summation xi with t for now, right? So you have t over theta minus n minus t over 1 minus theta equals 0, which just means that these two components are equal, which means that t times 1 minus theta is theta times n minus t. T minus t theta equals theta n minus theta t. The theta t's cancel out. What am I left with? Theta n equals t, so theta is t over n, right? And t was nothing but the summation. So average, right? Take the average. That's your MLE. Okay, and what is the Fisher information? You would have to take what? You can compute the variance, or you can do the double derivative and then take the expected value. Which one's easier for us to do? Usually, it's better to take the double derivative and then just evaluate it at the average, right? So double derivative minus t over theta squared. Oh, this is annoying. 1 minus theta, the minus goes out, but then you have another minus. So the minus stays, and then you just have 1 minus theta squared. And then you have the same thing, n minus t. Right? Okay. And then you can evaluate this at theta hat, which is the average. T over x bar squared minus n minus t over 1 minus x bar squared. Cool. What is t? Do we know? Can we write t in the terms of the average? Yeah, it's n times x bar, right? Okay, cool. We can get 1n right over here. We can take an n common, and you have 1 over x bar minus. And then what happens when you take an n common here? you get to cancel this out with this, right? And so then you have minus 1 over 1 minus x bar. Can we simplify this further? Yes, we can. We're done with the score. We don't need it anymore. And then that further simplifies to what? 1 minus x bar over x bar times 1 minus x bar. Right? Unless I've made a mistake. Seems like I have. I dropped a negative sign? Ah, yes, over there. Whoops. There's supposed to be a negative sign over there. So that would make the negative sign come out common. Minus n, 1 over x bar, plus 1 over 1 minus x bar, minus n, 1 minus x bar plus x bar over x bar times 1 minus x bar. This would cancel out. Then you have n over x bar times x bar minus 1. Right? Or am I missing something else as well? No, this should be right. Cool. Now this is your Fisher information. Try to evaluate this. Well, all you have to do is plug it in, right? And you plug it in into this test statistic, and you assume that this it shares the distribution of the standard normal.
If this is the second derivative, you need to take the negative to get the Fisher.
Right. I have to flip it again to get the Fisher information. Correct. So this would be 1 minus x bar. Okay, so there's okay, so whatever. Times minus 1. So Fisher information from double derivative. Okay, cool, that settles it. My mic's been off for quite a while now. It has been dangling on my floor, on the floor. Okay, that's your Wald statistic. You could do a similar thing for your score. The only difference is now you're taking the expected value instead of just doing the double derivative, right? So you will do the double derivative, but then you would compute the expected value at the given hypothesis. So at your theta naught, you would plug it in, and the rest stays the same. According to the score stat, you just have this n times the Fisher information. Cool. Likelihood ratio. Let's see if there's an example here. Oh, one good point that I forgot to mention. The likelihood ratio test works for non-normal distributions. Why? There's no normality assumption that we made, right? Every single distribution has some sort of likelihood, right? So it works for non-normal distributions. We don't have to worry about anything, right? And there's an example as well, I believe. Yes, the exponential. It's worth a look. It's pretty interesting. Cool. LRT for one parameter is I guess they don't talk about it. But if you have a single parameter, you usually take the MLE as your denominator, right? If you have multiple parameters, then you have to account for the case where the parameters are different. So that's your alternative hypothesis. And your null hypothesis is that the two parameters are identical, in which case the likelihood function will take that same mu, right, in this case. I don't have time to go over this in detail, unfortunately. So I'll be handing it over to Bob. And if I have time, I'll plug in these examples into the document, so you have something consistent. Cool. 5-minute break, and then I'll hand it over to Bob.
This is going to be the last portion of the review seminar. So let's go all the way back. All right. So we're going to start off with hypothesis testing. There isn't really much intuition to be given here. It's just using the sampling distributions you get for all of your parameters, and then it's testing on those. The nuance there isn't that much nuance, honestly. The theory and the concepts are pretty simple. It's just you're manipulating the sample distribution, and you're trying to get it into some known distribution so that you can see how likely it is to occur within that distribution. But let's start with the equality of variance. So suppose we have two independent populations, and we want to test if they have equal variance or not. Then we use the following test statistic. We take the sample variances, and then we divide them by their actual variance, and we divide them basically. We take the sample variance of population X divided by its true variance, and the sample population of population Y, or sample variance of population Y divided by its true variance. And this is just telling us that we get the F distribution. I believe the proof that it's F distributed it's done before the midterm, but it's in one of your week 1 to 5 slides. But the first thing that comes to note here is that we're testing what the true variances are. Like, we're trying to test that they're equal or not. So this statistic is utterly unhelpful because it has the true variances in there. So we could technically never calculate this. And so the one nuance that comes with these sort of hypotheses is that when we do a hypothesis test, we are actually taking this true sort of statistic distribution that has unknown elements. And then our null hypothesis is us making assumptions on those elements. So we can't calculate this true F distributed statistic. However, under our null hypothesis, we claim that they are equal. And so once we claim they are equal, then they just happen to cancel out. We can set them to the same thing, they cancel out, and it just happens to be the sample variance of X over the sample variance of Y, and that's the same F distribution. Now, once you have this test statistic, you can compare it to your rejection region. If it lies inside your rejection region, you reject your null hypothesis. And if it's not in your rejection region, then you don't have to reject your null hypothesis. You fail to reject it. And if you remember, our null hypothesis is that they are equal. So if we fail to reject, that means that there's sufficient evidence to say that the true variances of both populations are equal. If we do reject, we claim the alternate hypothesis. There is significant evidence to point to the fact that they are not equal. Now, if we look at this rejection region, you can see, for one, it's split into 2 parts. But for another, we're doing alpha divided by 2. So what this is telling us is that we're actually doing a 2-sided test, or a 2-sided test. The other indication of this is that we're using for our alternative hypothesis not equal to, right? If you remember, not equal to is the same as testing for both greater than or less than. Because if you have something, where's my chalk? If you have something where, I don't know, if you have H alpha is equal to the variance of x squared is not equal to the variance of y squared, this is equivalent to testing that both this is the case, or either this is the case, or this is the case, right? Because if it's not equal to, it has to be one of these two. And so in doing that, we can actually split our rejection region in two. Now, as I have it written here, there's two typos I've written here. One of them was intentional, the other one was not. The first typo, which I will correct right now, is that these two, the less than and greater thans, should be flipped. So if we are testing for HA of x squared should be greater than y squared, that gives us the rejection region of negative infinity to f. And then if we were testing for less than, then it's f to infinity. Now then, there is one more typo that I have left in here, and I want to see if someone can notice it. Let me just zoom in a little bit so it's actually possible to look at it. There you go. So swap these two, swap the inequalities. But there is one more typo I have accidentally put in to these rejection regions, and I want to see if anyone can notice it as well. Yes. Yeah. So I mentioned earlier that our not equals to, this is a two-sided test, which means that our rejection region, that sort of alpha level confidence, or maybe 1 minus alpha confidence, depending on what you want to say, is split between both of those regions, which is why we're doing the divided by 2. However, once I collapse it down to just these inequalities, these become one-sided tests. So rather than doing 1 minus alpha over 2 and alpha over 2, they should instead just be alpha and 1 minus alpha, I think. Yes? Yeah. So yeah, are we going to send them this PDF? All right, I'll fix that when we send the PDF. But yeah, intuitively, it makes sense then that when we want to consider either or of these, we're just combining the rejection regions, but then we're accounting for too little of our data, and so we instead expand our regions and we account for alpha over 2 instead of just regular alpha. Now then, for equality of mean, it uses something similar. We are testing for whether the means are equivalent or not. And for that, it is actually the same as testing for the difference between the means is equal to 0. Now, why is this convenient for us to test? Because if you remember, before your midterm, you guys probably went over, I think it was the t-test. Is it the t-test? It might be. It's the test for just the mean for a singular distribution. And in there, we claimed that if you took something like the sample mean, which is x bar, minus the true mean divided by, what was it, the standard error? Yeah, divided by the standard error, which was something like, that squared over n. There. We claimed something like this was your original test for the mean of a population. Well, when we do this, we're actually doing the same thing. Recall one of the first things that you guys learned about normal distribution is that if we have independence between our populations, then linear combinations of those independent normal distributions are still normal. And so that includes taking their means, right? Their means would be independent if the actual populations would be independent. And then we abuse that. And we say that if x bar and y bar, which have those distributions, are independent, then x bar minus y bar is in fact also normally distributed. And using that, we can just do the standard sort of definitions for variance and mean. Their mean, linear combination, we can just directly subtract them. And then their variance is not quite linear. You have to do the square of the coefficients. So instead of subtracting them, you would add them. All right, this is, I guess you could call it plus -1 squared. And then that just cancels out to nothing. Squared y m. And now, this itself is its own statistic. It's also normally distributed. And that is where your test statistic comes about. And then, using the same logic, we have our two-sided rejection region. And we can also use the same logic for greater than or less than. We can split that rejection region into its two halves. Furthermore, they give you a confidence interval for this. The confidence interval is below. It is the difference between their sample means plus minus the Q norm for 1 minus alpha over 2 times the square root of their sample variances. Now, I want to kind of take a pause here. I think Malhar mentioned it earlier when he talked about margin of error. But there is an important intuition that comes about with confidence intervals that I think it's less useful for this class, but for those of you who want to pursue statistics, after B57, it is useful to understand what a confidence interval truly means. So, how many of you have heard of the empirical rule, or some people call it the 65, 95, 99.7? Anyone? There's one. Anyone else heard of it? Yes. Okay. So a few people have heard of it. The empirical rule basically states. Let's see. Empirical rule basically states that 65% of your data is within 1 standard deviation of your mean. 95% is within, oh, I spelled within way off. Within 2 standard deviations of your mean. And 99.7% is within 3 standard deviations of the mean. So what does that have to do with the confidence interval? Well, when we did this, does anyone actually remember what z of, let's say we had alpha equals 0.95. What is actually z of 1 minus alpha over 2? Does anyone remember? Off the top of your head? It's something that you'll probably work with a lot. It's 1.96, right? And that is to contain 95% of our data. That 1.96 looks awfully close to the 2 here. And in fact, this is just stating that 97.5, because we're doing the alpha over 2, should be 0.5, pardon me, percent of our data is within 1.96 standard deviations of our mean. So what am I getting at? Let me raise this up so that people can see it a little bit more. What I'm getting at is that all confidence intervals, and once you get to multivariate statistics, confidence regions, they all follow the same idea, where you are taking your estimated test statistic, and I say estimated here because with any good estimator, the expected value, the mean, should be the true value. So any estimator plus the number of standard deviations you are away to encompass whatever percentage of the data you are considering. So if you are considering, 95% of your data, you want to choose enough standard deviations so that you contain 95% of your data. And then what are those standard deviations? Well, if you recall, your standard error of some estimator t is just the square root of your variance of t. Now, t has to be estimated here, but it's the estimated value of your variance. So what standard deviation is, it is actually just your estimated standard deviation. So what we're doing is we're saying we want to be this many standard deviations away. Here is our best guess for what our standard deviation actually is. And here is our best guess for what the mean is. And then if we take this confidence interval and we have, however many samples we have, we keep taking it, then on average, it will contain our true parameter. And that's sort of the intuition behind a confidence interval. All right. Now, for equality of mean testing, I gave this distribution here, I gave this statistic here. But one thing kind of is left to be decided. Now, if you remember, when I talked about equality of variances, all we cared about were the sample variance and the variance, which were, and then once we made our null hypothesis, that variance just disappeared, and all we cared about was sample variance. But when we go to the mean testing, you notice that we now have to consider both the sample mean in the form of our x and y bar and our true population variances, which means we actually have quite a few cases for how this test statistic, what this test statistic turns into. The first case is that, well, firstly, let's go for all the cases where our variance is unknown and we would have to estimate it. The first case is that they are equal. Under the null hypothesis, we're including the fact that our variances are unknown but likely to be equal. Since we don't know, we have to estimate it, and they give something called a pooled variance. Now, pooled variance is saying intuitively, what if instead of considering the individual variances, what if we just added them together and we considered it as one big sample? In fact, if you break down the variant, that equation there, right, remember that there's m values for population y, n values for population x. The sample standard deviation for population x is just 1 over n minus 1 sum of, x bar minus observed x squared. I think I'm doing that right. Or it might be reversed. I don't think it matters, but I'm going to do this. And then the sample standard deviation for y is 1 over n minus 1 sum of yj minus y bar squared. So when we multiply both of those by n minus 1 and m minus 1 respectively, we're getting rid of these coefficients. And now, if we combine them, we actually have a population of n plus m, right? Well, and then to account for unbiasedness, we're subtracting 1 from each. So that's where that n plus m minus 2 is. Recall that n plus m minus 2 is just equal to n minus 1, plus m minus 1. So what we're essentially doing is we're saying, let's not consider these estimated standard deviations or estimated sample variances on their own. Let's take out that divisor and let's try and group them together. And so the pooled variance is doing this. It's saying, what if we considered it as one big sample, and what if we took the unbiased estimator for that one big sample? Now, using that, assuming that our test statistic, all the variances are equal, then we can factor out the standard deviation, and then we can replace that standard deviation with our estimate. And this changes it. This changes our test statistic, rather, from a normal distribution to a t-distribution with n plus m minus 1 degrees of freedom. Why is it t-distributed now? Because the normal distribution relies on the fact that the only two things we're estimating are our sample means. And so using that, we can abuse the linear combinations of normal distributions rule and claim that our test statistic is normally distributed. But now, once we're estimating sampled variance, the pooled sampled variance rather, we now have one extra thing that we are testing. And so we can no longer use normality because not every statistic we're calculating there is normal. Sure that x bar is normal and that y bar is normal, but SP is not even close to normal. And so we now have to include this. And with SP, notice we have to use n plus m minus 2 extra variables to calculate. We now introduce those n plus m minus 2 degrees of freedom. And that's where your t statistic comes from. But from there, it's kind of just a plug and chug. You get your variance. You might have to calculate pooled variance on your own, or it might be given. Honestly, pooled variance is a really obnoxious thing to calculate. It's very likely that in your exam, they're going to give you something like your two populations and your two sample variances, and they might ask you to calculate pooled variance based on that. Yep. Any questions? Nope. All right. Now then, case 2, for where they are not equal. If they're not equal, we can no longer use pooled variance, unfortunately. So if they're not equal, we just take the simplest route. We replace our true parameters with their best estimates. Again, we're introducing new things to be calculated, so we no longer have our normal distribution. We now have a t-distribution, and the degrees of freedom is very obnoxious. It is that horrible number. That ends up looking pretty small, so I'm going to write it up here. The degrees of freedom for unknown lambda x not equal to, or sigma x not equal to sigma y is equal to, let's see here. Okay, is equal to the sample distribution of x squared over n plus the sample variance of y squared m squared, all that divided by, oh my god, okay, sample variance squared divided by n over n minus 1 plus, I'm missing a squared here, y squared m squared m minus 1. Yeah. So here, that's it written out a little bit bigger. I'll erase the thing right above it so it's not that confusing. There we go. The proof for this is very long, very arduous, and very pointless. But yeah, we run with this standard deviation and these degrees of freedom. It's worth noting that when you calculate this, you might get a decimal value. For degrees of freedom, there are two ways you can kind of interpret that. Within R, I'm pretty sure R will let you put in decimal degrees of freedom. But if you want to be precise, or if you want to say like, whatever context for your analysis doesn't require there to be a decimal degree of freedom, you can just round up to the closest whole number. Yeah. Now, along with these two, we need to introduce kind of a nuanced version of this population parameter testing, and that is the paired data test. Now, the intuition behind the paired data test is that suppose maybe you're a hospital and you're testing out a new treatment. So you have, your population X is your patients. Maybe patients before treatment. And what is Y? Y are those same patients or actually, I'm not going to say same because they could be different, but patients from the same population, I guess in our case, same hospital, after the treatment. So when we do these paired data tests, we're actually testing the effects of something on our population, whether that be, in our case, I'm using the treatment example. It could be, maybe some major event affects a population, but we're testing that this event or this thing that has been done has had a significant impact on our population. The easiest way we can do that we just take their means and subtract them. So we claim that for each observation, the difference between them, for each observation of x and each observation of y, we claim that the difference between them is also a random variable. These two are random variables. It makes sense that this is a random variable. But you might think, and I still have it on the screen, that this looks a lot like what we literally just did with the mean testing, right? If I were to do d bar is literally just x bar minus y bar. So why aren't we using that test statistic? Well, it's because if we scroll all the way up, the thing that we needed for equality of variance and equality of mean is we needed the idea of independent populations. These populations are clearly not independent. I even mentioned earlier, they could be from the same hospital, could be the same patients, just before and after some treatment. They clearly depend on the other, right? The value, maybe you're measuring patient height. The value of your patient's height before and after some chiropractic treatment clearly depends on what their height was before that treatment. And so we can no longer abuse this sort of independence. So our test statistic looks very similar. We use the fact that x minus y, right, this is equal to d, is still normally distributed. Now, our mean is not affected. Our mean is still, I believe, mu of x. Oh, I did not give myself enough space for this. We still use the fact that it is technically normally distributed. Mean of x, mean of y. But what is our standard deviation? Right? Our standard deviation is no longer clear because if I were to try, or sorry, not standard, variance. Because if I were to say, well, what is the variance of x bar minus y bar? I'll say this is the variance of d bar. Well, it equals to the variance of x bar plus the variance of y bar. This is stuff we've all looked at. And then now we have to do plus 2 times their covariance. Yeah. And this covariance, probably you're not going to be given it. You might run into a question where they give you specifically that covariance, and you use that to calculate your variance. You use that to calculate this. I should say that this is equal to, SD squared, and then put our estimators on there. Yeah. Right? You might be given this covariance, and you have to specifically calculate this, but my better guess is that you might just be given 2 values, and then you have to calculate their difference, and then treating that difference as its own variable, you calculate the sample variance for that variable. So when you get to a question like this, it's very likely that the hardest part of the question isn't going to be, figuring out the test statistic. I think this is the one test you guys have probably done far too many times. It's going to be finding out what that sample variance is for your difference. So that's something that is worth watching out for on your exam. Just all the different ways that you calculate it. I think this equation specifically, don't be scared to use the formulas for variance, because sometimes people get into this sort of weird lock where they say, oh, I have to use the equation given to me. I have to do this. I have to assume that the sample variance is given to me. But if it's not given to you, or if they give you something where you cannot use your formula, I think you've all taken the midterm, you've probably had to go through this. You have to figure out all the other ways you could arrive at that same variance and what that variance actually means. All right. I'm a little bit short on time, so I'm going to move on. So now I'm going to cover sufficiency and consistency. Now, with sufficiency, I'd say I don't know how much sufficiency you guys are going to cover on your exam. I think at most you might have to prove something with the factorization theorem. But a sufficient statistic, or a statistic that is called sufficient for some parameter, intuitively is something that contains all of the information that the parameter would have. So a statistic itself is just any equation you make with your observations, and that statistic is sufficient if it contains all the same data. Now, the intuition behind this is that, of course, your population contains information about the parameters of that population, and so you can say that something is sufficient if you are calculating a statistic with that data and it's preserving all of the information you need about your parameter. It's hard to grasp the intuition behind it, but luckily it's, mathematically it boils down to just those two theorems. It's sufficient for some parameter, factorization theorem, if the joint distribution function factors out to something that only uses those observations, being h, and then some function g that is only using your test statistic and the parameter. So I think there's not that much, sufficient statistic doesn't appear too much in later stats courses. It's something that you maybe know in the back of your head, but for now you can just understand that it's something that factors out cleanly from your joint distribution when you're looking for a certain parameter. Now, on to something that I think is more important, and that is consistency. Consistency comes in many different forms, but they all sort of rely on the idea of convergence, and that is convergence to either the true parameter or convergence to some zero error. So in that way, we can say that an estimator T is a consistent estimator in probability if T given n being the number of samples we're using to calculate T, converges in probability to our true parameter value as we increase n. Now, with this comes two lemmas, Slutsky's lemma and the continuous mapping theorem, which state that these are actually just regular results in analysis. It states that if you have two statistics that are calculated based on sample size n, and they converge to x and y in probability respectively, then their sum will converge to x plus y, and their product will converge to x times y. Continuous mapping theorem says this in fact applies for any continuous function. So if g is a continuous function, and we know that x approaches our true parameter in probability, then g of x approaches the g of our true parameter. The proofs for these, by the way, if any of you ever dared to take B43, I think that's Intro to Analysis, or maybe even in Calc 2, but it's normally an analysis topic that you will probably prove Slutsky's lemma and the continuous mapping theorem in one of those courses. So for now, you can consider those courses, or the proofs for these, to be maybe slightly out of scope for this. And in fact, it's not just probability, it probably converges just overall. Now, something that is more important, I think, because convergence and probability is very finicky to deal with. It's dealing with limits, it's dealing with probability functions. People tend to use MSE consistent in place of consistency and probability. And that is to say that the mean squared error, that your estimator Tn is MSE consistent if the mean squared error of Tn approaches 0 as n approaches infinity, which is to say intuitively that the more samples in our population we consider, the higher that n goes, the less the closer we are to that true value, our error gets lower and lower. Now, with consistency, there is this question of how do we relate to other things we learn? Because in short, sufficient statistics and consistent statistics, they're all really measuring the quality of our statistic, the quality for some estimator that we have. Like, how good is it? And it's kind of easy to get caught up between all these measures. So before the midterm, we went through things like unbiasedness, biasness, which also use MSE and MSE being 0. But there is a very important difference. And I think I only really have time for one example, so I'm going to leave you with an example of a difference between something that is unbiased, like an estimator that is unbiased, but an estimator that is specifically not consistent. So if you remember way back a few months ago, for the review seminar for your midterm, I gave a really silly estimator. I said you had something like your population, you sample, x1 to x5 from some population. And we want to estimate the mean, right? And I said, well, I claimed rather, that t equals x1 was an estimator. And more than that, I claimed it was an unbiased estimator. We prove this because clearly the expectation of t equals expectation of x1 equals mu. All right, this is kind of given. And so we knew that this was a unbiased estimator, right? Therefore, unbiased. And then we showed also that the MSE for this estimator is horrible. It's really high, and it doesn't really go down with n. So that's why we prefer to use more estimates. But now I want to say that let's find the MSE of this, right? Remember, the MSE is just the variance of our estimator, which is the variance of x1, which equals sigma squared. Now, you might notice something. Sigma squared here, right, this is the MSE. T. Sigma squared here, what important thing doesn't appear in our MSE? It's something that doesn't really matter when we're doing unbiasedness, but for consistency is very important. Anyone? Yep. Yeah. And this MSE does not depend on n. And that's kind of the point I'm getting at here, where something is MSE consistent, remember, if n goes to infinity, this MSE should go to 0. If n goes to infinity here, right, MSE of t equals sigma squared doesn't approach anything. It approaches sigma squared. It doesn't move with respect to n. So this is an example of a variable that is both unbiased, or it is technically a legal variable. It is, or a legal estimator. It's unbiased. Like, you could use it. It has a mean squared error, but it's not consistent. So these are the things that are kind of good to measure, or good to remember, is that there are stark differences between them. And more than that, you can even say that anything that is MSE consistent probably depends on n. Like, when you have an estimator that's MSE consistent, you can almost guarantee n appears somewhere in that estimate. Yeah. Here's the example down here. I just use m in that case. And then we go back to Fisher and score, which Malhar's covered. So I can answer questions about this, or we can do an overall Q&A with Malhar and Anaki, if anyone has questions. No? Sweet.